Today we're going to be talking about angular and linear speed. And so as we begin, the linear speed, it's the speed a particle is moving along the arc. Okay, so basically it's how fast, if you think about it, this is how fast a runner is running around a track, or this is how fast the end of a record player, not that you know what that is these days, but is moving, how fast that point is on there. Or how fast, if you get a piece of gum stuck on your bike tire, how fast is that piece of gum traveling around the tire? And so the linear speed is equal to the arc length divided by the time. How fast is it going? What's that length divided by time? And if you remember from earlier this year, last semester, we described arc length when it's in terms of radians as theta times r. And so this is theta times r over t. When theta is in radians. Okay, if it's not in radians, then you need to either adjust, you may remember the formula, let me write that on a piece of paper. If arc length is equal to theta over 360 times the circumference, 2 pi r, that's when theta is in degrees. Okay, so you could look at, if you were to do this formula here to find the linear speed, instead of theta r, you could use this whole formula here. If you were so inclined, times radius over t. No, this whole thing divided by t would be the linear speed. Keep it all in radians and life will be easier. The next thing, the angular speed is, measures how fast the angle changes. Okay, an angular speed is just going to be equal to theta over time. How fast is that angle changing as a function of time? Now notice this linear speed is equal to theta over t times r. So what we can do here, the linear speed is just equal to the angular speed times the radius. So notice angular speed right here, theta times t, shows up right here in this formula, and this r is just the radius. So this is often very helpful. Okay, so I have a couple examples that I want to work through. The first one, a 15-inch diameter tire on a car makes 3.9 revolutions per second. Find the angular speed. Okay, so angular speed is just theta over t. So you've got kind of two options on how to do this. The first one is, well, we don't know theta, we know how many revolutions. So we can convert revolutions. One revolution is 2 pi radians. And that equals 18.6 pi radians. Now it told us that it's doing this per second. So now when we look at the angular speed, and I have found it to be effective to write out those words. I don't have a shorthand for that, and it keeps me from getting confused later if I go ahead and write that whole thing out. Angular speed is equal to theta over time. Well, the theta was 18.6 pi over the time, this is radians, over 1 second. And so the angular speed is 18.6 pi radians per second. Another slightly different way, but same idea that we can use over for this one if we'd like, is to think about this is doing 9.3 revolutions in 1 second. And I can just set up a proportion and say, well, 1 revolution is 2 pi radians. And now the revolutions are going to cancel here, and I have 18.6 pi and now I'm left with radians per second. And I ran out of space, but radians per second. And so this is another way my units for linear speed are going to be radians per second or radians per some unit of time. It can be seconds, minutes, hours, days, years. I don't really care. But this tells me that I've gotten things into angular speed. So then the next part, they say find the linear speed of the car. Well, the linear speed, if you remember from a second ago, is the linear speed. The easiest thing to do is just notice the linear speed is equal to the angular speed times radius. Well, we already have the angular speed, and we can just multiply that by the radius. Notice, too, they said it's a 15-inch diameter. That catches me more often than I care to admit. So, sorry, you'll find it in my answer keys wrong, but whatever. So if the if the diameter is 15, then the radius is 15 over 2, or 7.5. So the linear speed is equal to the angular speed times the radius. Okay, so that's 18.6 pi radians per second times a radius of 15 over 2, which is equal to 139.5 pi, which is approximately 438.25 inches per second. Okay, because that was in terms of inches, and our time is seconds. Okay, we could also plug everything we want into this formula, theta, and then r, and then t, but I really much prefer doing this right here. Okay, the next one is a true story about me. I mean, I kind of manipulated it for a math problem, but I really and truly did fall off one of these merry-go-rounds when I was 4 years old, and I broke my collarbone. So my dad and I tease each other. He tells me I just couldn't hold on very tight, and I said, "Dad, I was 4. You pushed me too fast." So anyway, it's all happy. It's all good. But anyway, I did break my collarbone. So the point in this problem is, what we're saying here is that my sister, I don't remember exactly, I was 4. I don't remember all the details of the situation. But in our problem, my sister is sitting 2 feet from the center of the merry-go-round. So if this is the center, she's 2 feet here. So I'm going to draw this circle again in a second. And then I am at the edge. I'm 6 feet from the center is kind of what I said. Let's draw that a little better. So if this is our merry-go-round looking down, here's the center of the circle. My sister, Laura, is about 2 feet from the edge here, and I'm somewhere, not 2 feet from the edge, 2 feet from the center, and I'm somewhere out here, and this is 6 feet right here. So then they tell us how fast she is going. Notice, and they want to know how fast was I going when I fell. Okay, so if you think about it, this whole thing is turning together, right? So if you're standing at the center, you turn, but you're not moving as quickly as you would be if you're way out here on the outside. So with Laura, somewhere about here, she's turning in a circle kind of like this, and I'm turning in a bigger circle, but we do a whole revolution at the same in the same amount of time. Okay, so what we have here is that Ms. Kosh's, that's me, Ms. Kosh's angular speed needs to be equal to her sister's, it needs to be equal to Laura's angular speed. Okay, but our linear speed will be different because she's going all the way around. I guess I could have put it on the same little thing. You can kind of see where she is. She goes around at the same amount of time that it takes me to go around, but you'll notice the path that she's traveling is a shorter path than the path that I'm traveling. Okay, so the way that I would work through this one is to say, they told us that Laura's traveling at 4.2 feet per second. So that's her linear speed. You know what, let's call it Laura's linear speed. And that's equal to her angular speed times her radius. Okay, they tell us she's moving 4.2 feet per second. We don't know the angular speed. But we do know that she is 2 feet away. Okay, so I guess I should label things. This is feet per second. This is feet. So when I divide that by 2, her angular speed is equal to 2.1 radians per second. Now, I am traveling at the same angular speed, but my radius is a lot greater. So they needed to know what my linear speed is. Ms. Kosh's, I forgot that. Ms. Kosh's linear speed. And that would be equal to my angular speed times my radius. My sister and I were traveling. Here's our little circle again. Maybe, hang on. We're traveling the same, it's 1 revolution for both of us. And so we have the same angular speed, 2.1 radians per second. And now my radius is 6 feet. Okay, so this gives me 12.6 feet per second is my linear speed. Now, when I saw this, I thought, okay, fantastic. I don't really know what that means. So I went ahead and converted that a second ago to miles per hour. So granted, we made up these numbers. It's been too many years since I actually fell off. But if we have this 12.6 feet per second and I convert it, 1 mile is 5,280 feet. For every second, there's 60 seconds in 1 minute, there's 60 minutes in 1 hour. I converted all of this and I got that I was going just over 8.5 miles per hour. So when I fell off. Who knows if that's true? I tried to make the numbers somewhat reasonable. But I hope this kind of helps clear up angular and linear speed.